All right. So I made a problem similar to your problem. I added some extra rooms and some extra doorways. I took away a doorway. So um, anyways, this is my floor plan. Is it possible to find a circuit through the house that uses each doorway once? So notice the word circuit. Circuit means it has that same root word as circle. So that means that can we start in one spot and then go through all the doors and come back to that very spot? And see how they said it goes through each doorway once. So that's also known as an Euler circuit, right? So what they're really asking this question is there an Euler circuit in this graph? And one of the most crucial parts of this is even though this is like a floor plan, what we need to do is kind of transform this into more of the edges and dots graphs. Because really, we're not really interested in the shape of the rooms or anything like that. And actually, the rooms are actually our vertices, our locations, and the doorways are the edges, right? So we can make our graph. This graph is going to have A, B, C, D, E, F, G, H. So it's 1, 2, 3, 4, 5, 6, 7, 8, 8 vertices. And the question is, what will it look like? So I'm going to make all the vertices and try our best to do this picture here. Maybe I'll do D over here. All right, and then I have all the different rooms. And they're kind of thinking as D, even though it appears like D is like probably, you're thinking about D is like the backyard, but no, D is just the outside of the house, period. So whenever you leave one of these doors, let me highlight them for you. So whether you leave here, 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 or here, you're leaving to the area D. So that's just represented by just one dot here. So to make that clear here, D is just outdoors, okay? And we're not specifying like backyard outdoors or front yard outdoors, it's just outdoors, which is represented by one dot on my graph, D. That's a bit confusing. So, okay, so let's draw in all our dots here. So I noticed that we could just start with B. B is connected to A and C there's one door to A, one door to C. So let's go ahead. B is connected to A and to C. Okay, so I did these two doors, A to B, B to C. Okay, and then B also has two other doors leading to D. So there's actually two doors here, one right here, and one, we'll just say right here. Okay, so see how that represents these two doors right here, here and here. There's two ways from B to D. Right, and there's one way to A and there's one way to C. Okay, so that looks good. All right, let's focus on the next vertex. Let's focus on C. C, you can go straight from C to A, which I don't have on this graph yet. So I'm going to draw straight from C to A. But then also there's from C to B, which we've already drawn on. So we have to be really careful about this, that we don't draw doorways that we already drew. So you already have a connection, and there's only one between B and C, and there's only one, so good. Now I notice, look at the other two doors. There's two connections from C to D. So I've got to draw from here over to D, from here over to D. Now I could have drawn them going the other direction around A, but remember all that matters is we can go straight from C to D. So we did that. All right, let's look at A. From A, we've already said from A, we've drawn a line to B, which we already have there. And so wait, I'm thinking about these four doors from A. 1, 2, 3, 4. There's four doors leading out of A, and we just need to make sure that we have all of them. So we have the one connecting A to B, we have that already. We had the one connecting A to C, we have that already. But do we have the one connecting A to D and one from A to G? So we need one from A to D, which is A to D. And then we need one from A to G. So A to G. There we go. So I think we have all four doors from A. Right? Then we're going to move on to E. And I'm just kind of going in a haphazard manner, I guess. Don't have any great order. From E, we can go see the door from E to G. So I'm going to draw a line from E to G that we don't have yet. Then from E to F. So there's a line from E to F. We didn't have that yet. And those are the only two doors from E. All right, moving on to the next. 1F. And it'd probably be good if I, like, one by one, I crossed off as I go through each vertice and make sure to get them. So we know which ones we've done. So we're on F. We need to make sure there's a door from F to E, or a edge from F to E, which there already is, and F to H. So we draw one in. So that's F. F has all its doors. Now let's focus on H. H needs a door from F to H, which we already have, and then we also need a door from H to G, which we do not have a connection straight from H to G. So I'm going to go draw that in. So we're done with H. Okay, let's focus on G and make sure we have all the doors for G. From G, we should have, we should go straight to A, which oh wait, no, sorry, I'm just going to go from top left, going counterclockwise here, like so. That's kind of good for me to keep an orderly, tried my best to keep an orderly part about this. So notice how we have, I'm looking at G and I'm looking at, we have this one, this one, this one, and this one. So I'm going to go, rather than randomly kind of going down, then to the left, and this down and down, I'm going to try to do this in a clockwise manner. So like, counterclockwise. So I'm going to start with this one, then we'll do this one, and this one. And that's all the doors from G. So G has a connection to D. No, it currently does not. I mean, it looks like it does, but it goes through A. So like we're going to go from G straight to D. Okay. Then G has a connection to A, which we already have drawn, and there's only one. So we already drew that one. Okay, then G to E, which we already drew. Then G to H, which we already drew. So we're good for that one. Okay, we can see the four doors from G, 1, 2, 3, 4. And on the graph, 1, 2, 3, 4. So we're good. G is done. All right, I think the only one, 1, 2, 3, 4, 5, 6, 7. I think we have just one more, and that's D. We kind of skipped to alphabetical order here, which would have been a good idea, but A, B, C, D. So we need D, E, F, G. Oh, and G should have been here, but whatever. That would have been a little bit better idea to do that in alphabetical order. But anyways, so let's do D. From D, we should have two doors in two ways to get to B from D. So we do, okay? Then from D, we need two doors to C. which we do have. Okay, good. From D, we need to be able to get to G. D to G, straight to G, yes. And then from D, we need to go to A. We go to A. Okay, so I think that's all the doors. Let's just highlight them. I'm gonna just highlight all the doors from D and make sure we have them. So they're here, 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 here. Those are all our pathways to D. So it's 1, 2, 3, 4, 5, 6, 2 to B, 1, 2, 2 to C, 1, 2, 1 to A, 1, and 1 to G, 1. And so I think we got it. That's 1, 2, 3, 4, 5, 6, which I think there's 1, 2, 3, 4, 5, 6. So it looks good. All right, so this is our graph. They ask us, is it possible to find a circuit through the house that uses each doorway? Once and only once. So to answer that question, you really need to focus on the degree of each vertices. So I'm gonna go around alphabetical order, A, and we're gonna count, look at the vertices from A. It's 1, 2, 3, 4. So this has a degree 4, which is an even vertice. It's an even vertice. Then B has 1, 2, 3, 4. So that is an even vertice. C has 1, 2, 3, 4. That's an even vertice. D has 1, 2, 3, 4, 5, 6. That's an even vertice. E has 1, 2. F has 1, 2. G has 1, 2, 3, 4. And H has 1, 2. So it does look like we do see the theorem says, and if you have all even vertices, that you do in fact have an Euler circuit. There is a way to walk around all this house, walk all the way through the house and go through every doorway once and only once. So now that we decided that we can do that because they're all the vertices are even. Even if we had just one odd vertex, we would have to say no to that question. But every single one is even. Okay. Remember, an even number is 2, 4, 6, 8, 10, 12, 14, and so on. Okay. All numbers divisible by 2 also. Oh, yeah. So now we need to actually find that one, and we need to use McFlurry's algorithm. Which would mean that we have to draw this out several times. My graph is a little bigger, and that would be a little bit more difficult to draw this out as we would have a lot of doors here. So I'm going to do my best just to do my shortcut way of doing this. And that is I'm going to highlight it as I go over that and I use up that edge. I'm going to highlight it. And we're just going to start anywhere that we want to start. And I'm going to go ahead and start from D just because that's normally what you would do when you go inside of a house. So I'm going to go ahead and start from D, and I think I'm going to go to the upstairs because it seems like I was thinking about the GEFH being like an upstairs place, but it's connected to the outdoors too. So, but anyways, I think I think I'm going to just go with, let's go from D. We'll start from D and then just try to go around. So yeah, I think I'm gonna go D to G. So we're gonna pretend there's like an upstairs balcony that we can go from the outdoors up to the balcony, and D, G, I'm saying. So I'm gonna go on this one right here. just so that we see, and I'm gonna keep track by writing down here what we went, where we went from where to where. So we started at D. Because this is the Euler circuit, I can like go, I could start at any vertice, but we do have to make sure that we end up at D. And that's going to be highlighted so that that leg is no longer there. I just wanted to make sure that this is not this is not a bridge. Remember, we can't go on bridges. But if we take this side, imagine taking DG off, from G, could we get to everywhere else on the graph? Yes, I could go around E, F, G, H, and then go down to the A, B, C. So I can get to everywhere still. This is not a bridge. So I can go ahead and go on DG. I'm going to write that, record it down by saying D to G. Then I'm going to highlight the next one. I'm going to go from G to E. And I'm just going to write that. Then now we're at E. Then from E, we only have one place to go. We only have one place to go from E to F. However, it's all connected from there. So like this is not like burning my bridge because from F, I can still get to everything else back in my bridge, back in my graph. Okay, so I'm going to E to F. I'm keeping track of each step. And I'm imagining that I've been erasing these, even though we can see them still, as I highlight them yellow. Okay, then from F to H. Okay, I wanted to go over what the definition of a bridge is. So look at like this graph. See how like there's lots of edges on this side and lots of edges on this side. But as soon as this person walks across this bridge, if he didn't go through all the edges on this side, let's say that part side is part A, and he crosses this bridge, then he has no way to get back to part A to, can finish off the rest of the bridges over there. So the idea is that of the graph, you don't want to cross a bridge. You don't want to burn your bridges when you're doing these Maclaurin algorithm and you're making your Euler path with the vertices that are still left, with the vertices and edges that are still left. So if he already, like I said, if he already went on all of these edges that we see in this region A, if he already went on them, then that's fine. It's like they don't exist anymore. And then we just think about this bridge and the rest of it and how this bridge would not like disconnect him from like from all of the vertices that are left in the graph. Okay. Well, I mean, I guess it would. Technically, it would still would be, well, um, it would it wouldn't really be, I mean, he would have to go on that bridge if everything in A was already taken up. So, yeah, I guess it would still be a bridge because it's disconnecting where the spot he was from coming to this one. But this place is actually forgotten once he leaves it, since if he doesn't need to come back there. Anyways. All right, so it's always focusing on what's left of the graph and asking, is what I'm going on a bridge of what's left of the graph? That's what we really need to be asking ourselves when we choose a side to go on. So back to my problem. I chose DG. That was not a bridge because we could get to all the other vertices. We could have gotten to G but via D, A, G. And we could have gotten to E, G, D via D, A, G, H, E, F, E, and stuff like that. So everything was connected. What did exist a route to get to every vertice from where we need to leave, or at least where we need to get to left, right? So we're going to continue going on, and G to E to F. So a lot like when I was saying like when we went from G to E, that wasn't a bridge because we could have gone from G to H to F to E. So we could have gotten to E still another direction, right? So that wasn't a bridge. We go to E to F. And I guess technically this is our first bridge we actually go over because, well, once I go here, I can no longer get back to E. There's no way to get back to E. But E is kind of forgotten about because we don't need to get back to E. So, and we only have one direction to go, so we had to go that way anyway. Same thing with F to H. We had to go there, and it sort of is, I guess, a bridge because we can't get back to E, and we can't, when we go from F to H, we can't no longer get back to F, but we don't need to go back to those areas because they already have all the bridges, they're connected. So it's fine for me to go across this. Same thing here. I'm going to go from H to G. And there's only one way I could have gone. Yeah, it is a bridge because I can't go back to H and F and E, but those places are all forgotten. So we're going to go from H to G. Then going from G, I'm going to go now actually going from G to A. This is a bridge. Of course, there's only one way for me to go from G back to the rest of the graph. And so as soon as I go across this, then I can't go back that direction, but that's okay because we already have everything in that area, right? So I'm going to go, oops, I'm going to go across AG. So we went from G to A. And now from A, I can go to C, B, D. And I'm just going to go ahead and go to C. And I don't think any of these would have been a bridge because A to C I could have gotten to everything else that is left to get to, right? We need to get to G, E, F, H is kind of forgotten because those are basically erased because we don't need to get to them anymore. So we're really focused on the A, B, C, D, and we need to not burn our bridges so that that all vertices that are left and edges that are left, we can still go on them. So if I take that away, I mean, the bridge that the graph that's left and the vertices that are left, we could still get, to B and A and D. So that's not a bridge. So I'm going to go ahead and go across that. So we're going to write it down A to C. Then I'm going to go, I can go from B, I can go from B to C because I can, if that's gone, I can't get to C anymore. Wait, yeah, I can. I can go back from D to C. So I'm fine. I don't think that this is a bridge because um, with what is left and where we need to go left, like we need to go to C left. Yeah, we still need to go to C again. But we have a way to get there from D. We still need to go to A, but we still have a way to get there from B to A. And then we still can get to D from A to D. So it looks like I'm fine just going on this. It's not a bridge. It's not essential because A, C, D, and are all still connected via roads. So, if you think about it, look back at that picture, like we just have to make sure that, that one of these vertices is not like an island where there is no roads to get me there. If it is one of the vertices, we still need to visit because it has edges connecting it, right? So let me make sure that I write that down. So we went from C to B, Okay, then from C to B, I'm gonna go ahead and go to, let's see, if I go to A, then I guess we can go to A. I don't see any, because look at, if I go from B to A, I can still get, from A to D to B to C. I can still get to all the vertices that are left that we need to get to. If I go to A right now, right, I can still go to D, B, C. So let's go ahead and go to A. It does not appear to be a bridge to me because it looks like, we can go to all those locations still. So I'm gonna go to A. Then from here, I'm just gonna go to, I only have one place to go to, and that's D. So, but if I go from A to D, notice now that I can no longer go to A. But that's okay because we don't need to go back there anymore. So I'm gonna go to A to D. Okay, then I have to make sure that we have to travel to C and B still. So I'm gonna go ahead and go to B. If I go to B, there's still a way to get to D and C. So I don't see that that's a bridge. So from D to B. Now, from B, I have nowhere else to go. And I guess this is a bridge because it's going to block me from going back to B. But that's fine because I don't need to go back to B. And I have nowhere else to go. So I have to go on this bridge back to D. Okay, then I have nowhere else I need to go. I'm going to go to C. So I go to C. So D to C. And then let's just go back from C to D. And then there we go. That is our graph. Notice how that we started with D and then we came all the way back to D again. So we are beginning and ending at our same point. So that looks good. So what would that actually look like in our going back in our graph? And if we can now, if I can make this a little smaller so you can see everything. So what happened here is I went to D to G to E to F to H, back to G. Then I went to A because I already came through this door. So I went to A, then I went to C, then I went to B, then I went back to A, then I went to D out through that door. Then from D, I went to B, then I went back out to D and then went to C and went back out to D. So it looks like I did go through all the doors once and only once. And again, I just I just followed in pretty much a random pattern, making sure not to go on any bridge. That is, let me specify, a bridge of what is left of the graph to go on. And sometimes I had to go on bridges. I had no choice, but there we go. That's our answer. I hope you found this video valuable. Have a great day. Bye.